Okay, I think the recording has started. Okay. Okay, so let us continue. Okay, so maybe before we continue, a bit of updates. So as I already sent in the announcements, um, like every section, every chapter actually has you should know section now, and all the chapters are updated. Like even the schedule is updated with the references for all the lectures, and the tutorials are also available in the Moodle. So like also the reading for every week. So I did not put reading for the previous week, but I have added it now, so you can actually go check the reading for the last week and this week. So the reading for the last week is just reading about Gaussian distributions in Bishop, and for this week it's an article on generative versus discriminative classifiers, which will be a good supplementary for what we are going to discuss actually in the rest of the lecture. Okay, so let's continue. Okay, so before we stop our discussion on like maximum likelihood, logistic regression, and so on, so I just wanted to end with a quick note, which is basically maximum likelihood, okay, can actually exhibit severe overfitting for data sets that are linearly separable. Okay, so I will explain why. So remember that maximum likelihood solution occurs when sigma is equal to, like the solution is basically at the place where sigma is equal to 0.5, right? So now this is equivalent to W transpose X is equal to 0, right? So now I can actually keep on increasing the magnitude of W and still the line is going to be the same, right? So if you remember our discussion on the geometry of discriminants, right? Like, so if I have a bunch of data points like this and like this, okay, and let's say I find a line which perfectly separates this data point, okay? So now if this line is given by W transpose X, okay, and I'm maximizing the log likelihood, okay? So by updating the W, I could, if there's no constraint on W, then I could just keep on increasing the magnitude of the W, right? Like, so the magnitude doesn't affect the position of the line, right? Like magnitude is irrelevant. So what will happen is the magnitude of W goes to infinity. Okay, so now here is a, okay, so it has been a long time since we did poll. So we're going to do a poll now, okay? Okay, so now I have this problem, right? Like, so I'm going to, I want to do maximum likelihood with this very simple data set that I have. Like there are 4 crosses and like 5 circles. I find the line. The moment I find the line, the W blows up, right? Now, this is the question. So can I solve this issue by adding more data points? Okay, so we're going to do a template poll. So can I solve this issue of overfitting by adding more data points? Okay, so A for yes, B for no. Okay, I'm going to stop the poll soon. Okay. Okay, it looks like most of you have actually read the notes, so I'm happy. So, okay, or you find the answer by yourself, which is also, again, I'm happy. Okay, so 65% of you think that you cannot solve this problem by using more data points, right? So why? Simply because this is a linear, like the moment I assume that this is a linearly separable problem, like any number of data points that I'm going to add is not going to help me to solve this problem, okay? Now, how can I solve this problem? Like I cannot add more data points. So how can I solve this issue of W blowing up? Any ideas maybe in the chat? Okay, so I think some of you already are answering. So the answer, one easy solution that we have already learned in this course is to add regularization. Okay, someone is asking, can you explain why large W is a problem? Okay, so the problem is not just the large W. So the problem is when you do maximum likelihood, like the maximum likelihood doesn't stop when you found the line. Okay, it is just going to keep on improving the W. It's simply because you do W transpose X. Let's say you find W5, W is equal to 5, and it works. It has 100% accuracy. Like you would just keep on increasing the W because the magnitude of the W doesn't matter for the orientation of the line, right? So the moment you find the right orientation, you could simply keep on increasing the W to satisfy the maximum likelihood criterion. And you could actually go up to infinity, but you're still going to have the same line, right? So that's the problem. Is it clear? Okay. Okay, so you could add regularization, right? Like one simple strategy that we have already seen is like to add something like L1 or L2 and say, hey, you cannot like keep on increasing the value of W, like the magnitude of the W has to be smaller, right? So it's a simple solution. But there are also like other solutions, like which is basically the idea of like using better estimators than MLE. Okay. So far we have only seen maximum likelihood in the scores. Like so, probably after few more weeks, like we will see some other estimators which are better than MLE in this aspect. Okay. So I think this concludes our like discussion on uh, probabilistic discriminative models. Okay. So far in this course, like so we have actually seen a bit of discriminant based models, discriminative models, and generative models. Okay, so I think so now we are in a position to actually discuss the merits and demerits of these different solutions for classification, and also discuss when to use what, right? So we're going to look at the merits and demerits of the three types of classification. So one is discriminant based, then you have discriminative, right? This is f of x, this is p of y given x. Then you have generative, this is p of y, x comma y, right? Okay, so let's actually start with generative models. So as we discussed before, this is probably the disadvantage is this is probably the most demanding of all the three, because you are interested in like, or you're attempting to compute or learn the whole joint distribution. Okay, so now the another disadvantage is if x is high dimensional, okay, then you need a large training set in order to be able to determine the class conditional densities. Okay, so you need large training set to estimate p of x given y to reasonable accuracy. Okay, now these are the limitations of using generative models, but there is actually an advantage in using the generative model. The advantage is you can actually, given any data point x, you can actually compute p of x as summation over k, p of x given ck, p of ck, right? So you take the prior and the class conditional density, you sum it over all possible k, you get p of x, right? So now this p of x is a very useful metric because now given a new x, okay, if p of x is too low, okay, then that means that probably this data point doesn't come from the actual distribution we are interested in, right? So in some sense, if p of x is too low, then that particular data point might be an outlier. So you can actually do outlier detection easily by using generative models. All you have to do is compute P of X. If P of X is too small or negligible, then probably this is an outlier. So you can ignore that. Is that clear? Okay, so now let's actually try to compare generative models versus discriminative models. Okay, so remember that in the case of generative model, you try to compute P of X given Ck and P of Ck and use that to compute P of Ck given X, right? On the other hand, discriminative models are very simple. Like all they do is directly model P of Ck given X, right? So if our goal is just to do classification, then probably discriminative models are better than generative models. Okay, why? Because P of X given Ck might have a lot of structures which are not necessary for classification. So I'm going to give you an example. So let's look at this example. Okay, so now you see the P of X given Ck for class 1 and class 2. Okay, now you can see that for class 1, P of X given C1 is actually a more complex distribution than the second class distribution. It has two modes, right? So it's a bimodal distribution, okay? On the other hand, if you are interested in just the classification aspect, okay, so then the decision boundary that you would care about is this decision boundary, right? So the one that is also given the right side in green color, right? So now if you're just looking at coming up with a decision boundary, actually it doesn't matter whether the blue curve has two modes or one mode or three mode, right? So all it matters is like where is the decision boundary. So in other words, for example, this mode has no effect on the posterior probability. So the left hand mode of P of X given C1 has no effect on posterior probability. So in this case, you are actually spending way more time in coming up with like P of X given Ck, while you could have done a simple discriminative model, which could do the job for you, like for the same accuracy, right? So now this is one way to compare. Okay, so what do you mean by left hand? No, okay, left hand mode. So I mean this. So there are two modes for this distribution, right? So I mean the left hand mode. Okay, so now let's actually move to comparing discriminant based models versus discriminative models. Okay, so remember that in the case of, okay, where is it? Remember that in the case of generative models versus discriminative models were more simple because they were directly modeling P of X given Ck, right? On the other hand, discriminant based approaches are even more simple. So these are even more simple because even more simple. Why? Because in the case of discriminative models, you are modeling probability of Y given X, right? On the other hand, discriminative models have no probabilistic interpretation. They are directly modeling F of X, right? Or in some sense, this combines the inference and decision stages in classification. If you remember our first discussion about classification, there are two stages. First, computing the probabilities, then making a decisions based on the probabilities, right? Like in some sense, discriminant-based models combine both these stages together, okay? So the big disadvantage of discriminant-based models is there's no access to P of Ck given X. You cannot access the probability values in discriminant-based approaches. Like you directly get the score. That's it, right? Now, there are actually many advantages in using P of Ck given X. Okay, so I will try to list some advantages now. Okay, so the first advantage is the idea of minimizing risk. Okay, so okay, let's say my loss matrix is subject to change from time to time. Okay, so making, like, if you remember the loss matrix, like if you have CK classes, 1, 2, 2, let's say there are 5 classes, okay? The loss matrix basically tells what is the cost in misclassifying class 1 to class 2, class 1 to class 3, and so on, right? So now let's say that I work on an application where this loss matrix changes every day or for every few weeks, okay? So now in the case of, if you have access to P of CK given X, then going from P of CK given X to the decision is trivial. All you have to do is incorporate this loss matrix, and every day the loss matrix changes, I'm fine, because it's not the P of CK given X which is changing, it is just the loss matrix which is changing. And since we have these two stages separated in a discriminative approach, we can actually incorporate this easily, okay? On the other hand, if you are using discriminant based approach, if the loss matrix changes, okay, loss matrix changes, then you have to retrain the system from scratch again. Okay, now this is the advantage of having P of CK given X. So if your problem is in such a way that, for example, like if you're just using 0 on loss matrix, and the 0 on loss matrix is not going to change at all, then it's fine, you're good, right? On the other hand, like if you use a non-zero on loss matrix and this loss matrix changes every now and then having access to P of CK given X is actually more advantageous. Okay, okay. So then the second advantage that I could think of is compensating for class priors. Okay, so now let's consider cancer prediction, which we have seen recently, right? Like during the evaluation metric. Okay, now in this case, my data set is going to be heavily skewed, right? Like, so for example, like only 1 in 1,000 patients have cancer. So if I have a classifier which always gives no, this classifier is going to have 99.9% accuracy, right? So now this is the problem. Like, how do I solve this problem? So there is actually one solution, which is the most common solution in the literature, which is basically the idea of sampling the rare class more than enough. Okay, so basically you sample the rare class more, okay, and balance the class distribution in the data set. So you sample the, like, you sample the cancer class more, okay, and make sure that you have 50-50 distribution of both the classes, okay? So now using this new data set, you learn the posterior probabilities. Learn the posterior probabilities using the balanced data set. Okay, so once you learn this posterior, then you can actually compute the actual posterior. Okay, so let's call this as new posterior as old posterior divided by class fraction in sample data multiplied by class fraction in original data. So since you sample data, you are kind of balancing it again by dividing and multiplying. Okay, so now this easy solution of learning from rare classes can be done with discriminative models, but you can't do this with discriminant based models. Okay, so any questions about like this oversampling part? Okay, so what is meant by class fraction? So, well, like for example, well, like it depends on like which posterior for which class you are using. Like, so what is the like what is the fraction of cancer before sampling and after sampling? Like before sampling, it was 1/1000, but after sampling, it's going to be 1/2. Someone raised hand.
Hello?
Yeah.
Yes, thank you. I just posted a question in the chat. How to efficiently choose the decision boundary for discriminating models? Most of the time, I see that people choose point 0.5, and so why is that? How can we efficiently choose this decision boundary? And the second
Okay.
question, okay, I'll let you finish first.
Okay. Well, I think if you have like a binary classification problem, like with a sigmoid unit, 0.5 seems to be the most reasonable uh, guess or choice, right? Like, so for example, if you want to fine tune it further, one way to do that is to actually take the trained model and just fine tune the threshold based on the validation set. So you can move around zero point 0.5. You can move to zero point 0.6 and see if the validation performance is increasing. You can move to zero point 0.4 and see if the validation performance is increasing, and so on.
Okay, so for instance, for the assignment, we have to use the maximum likelihood for the Gaussian discriminant. So can we use 0.5 since it was not
Yeah,
okay, thank you. So
yeah.
now my second question, I'm a bit confused. How come that the Gaussian discriminant is not a discriminant models with the name discriminant, but is not a discriminant model?
Okay. Okay, so that's okay. So well, like it's similar to how logistic regression is not a regression model, right? So well, as the terminologies are kind of messed up, but we are using them for historical reasons. So
Because I can see that the
also,
G. Mhm.
also remember that GDA was discovered way before, like we had this idea of coming up with three categories of classification. So the authors of GDA would not have thought about discriminative models versus generative models versus discriminant based models.
Yeah, because when I read Trevor Hasty books, The Element of Statistical Learning, they call it discriminant model.
Yeah. Well, so well, like there are some confusions. Yeah, but I
Okay.
try to come up with like a unified way of calling things. So maybe I would differ a bit from the books. Okay, so okay, so now there's a question. Does oversampling leads to biased decision? Does it give us a misleading distribution? Okay, so it's not, maybe I'm not sure if it is the right thing to say it's giving you a misleading distribution because you're actually correcting for that when you're computing the final posterior, right? So you are making it 50-50 so that you can actually learn something useful, and then like you are also accounting for the fact that you changed the distribution in step 3 here. So I don't think it's a misleading distribution. Okay, so another very important question is like, why not undersample the non-rare classes instead of sampling the rare, oversampling the rare classes, right? Like, so like I think maybe different books would give different ideas, like, but my philosophy is like never undersample, always oversample, because like why throw away the data that you already have, right? So every data point is useful, so don't throw away the data that you already have by undersampling. So just go with oversampling of rare classes. That's a very good practical question. Okay, so maybe let's continue. So now, actually, there are many more advantages of using P of CK given X. Okay, so the third advantage we are going to discuss is combining models. Okay, maybe I'll move to the next page so that it's in one page. Combining models. Okay, so now let's say I have two features, okay, x1 and x2, or it could be two group of features, okay. Now P of ck given x1, x2 is proportional to P of x1, x2 given ck, P of ck, right? I have just applied Bayes rule here. Now, if I assume that x1 and x2 are conditionally independent given ck, then this becomes P of x1 given ck, P of x2 given ck, P of ck, right? So now this becomes, now I can actually apply the Bayes rule individually for these two terms, right? This term and this term. So this becomes P of ck given x1, okay, multiplied by, okay, so, and this is P of ck given x2, okay, divided by P of ck. Okay, so if you substitute Bayes rule, like you would see that there will be two P of ck's, one cancel with the numerator. So there's just one P of ck here. Okay. So what have I done here? So I wanted, like I had two classifiers. The first classifier, which is based on x1, the second classifier, which is based on x2. And I have an elegant way of combining the predictions of these two classifiers to come up with a single prediction. Okay. Now let me give you a practical use case for this, right? Like, so for example, let's say you are interested in predicting a particular disease in the patient. Okay. So now there are many tests to do this, right? Like, so there could be this group of easy tests, let's say 4 easy tests based on blood. And like you have a classifier which says whether the person has the disease or not based on this particular test sets. Okay, so that could be x1. Now the doctor feels that the patient has to do more advanced tests, so he could send them to the next unit where they're going to do a bunch of scanning and other things. Okay, so now that could be x2. Okay, and they come up with their own prediction of whether the patient has the disease or not. Now, if you have access to this class like P of ck given x, right? So you can combine them in an elegant way and come up with the final prediction of whether the patient has the disease or not, conditioned on all the tests that has been done. Okay, now this is not possible if you don't have access to P of x, like ck given x. Okay, so now this is another beauty. Finally, you could actually use this for a reject option. What is a reject option? If P of ck given x is too small for all classes, uh, maybe too small is a wrong way to say this. Like so for example, like if P of ck given x is uniform over all the classes, okay, which is the worst thing that could happen, right? So my classifier is saying, after seeing the data, my classifier is saying all the 5 classes are equally probable. What does that mean? That means that my classifier is not confident to make a good prediction, right? So in this case, you could actually say that your classifier could actually say that I don't know, or I don't want to make a prediction here. So the classifier could actually reject x when it thinks that it's confused between all the classes and there is no clear winner. Okay. Now this cannot be, well, it's very hard to do this with a discriminant-based model. Is that clear? Okay, so I think I would like to take a small pause here. Okay, so ideally, okay, you can guess that I kind of wanted to do the summary before the study break, but we were a bit behind in schedule. But we are going to do a summary of the entire course to get a big picture of like where we are standing. Okay, okay, so in the case of machine learning, like in the beginning, we discussed that you could either do supervised learning, right, where you have access to the label, or unsupervised learning. right? So we have seen one example for unsupervised learning, which is the idea of dimensionality reduction. Okay, specifically, we have seen TCA for dimensionality reduction, right? So now we have also seen dimensionality reduction in supervised setting, right? So we have seen dimensionality reduction in supervised setting too. And can someone tell me what that algorithm is? Chat. So what is the supervised dimensionality reduction algorithm that we have seen in this lecture, in this course? No. Fisher's discriminant analysis, right? Like so Fisher LDA. Okay. But other than that, we have also seen regression, which is another supervised learning problem, right? In the case of regression, we have seen linear regression, right? And we have also seen nonlinear regression. But the way in which we did nonlinear regression was by a hack. So we did that by using nonlinear basis functions. Okay. So now in the case of linear regression, the model was a linear model and the decision surface was also linear. Okay. So in the case of nonlinear regression using basis function, the model is a linear model. Okay. And the decision boundary was nonlinear. Okay. So the first L means it's a linear model. And this means it's a linear decision boundary. But I understand that the concept of decision boundary for regression is a bit misleading. So let's actually move to the classification setting. So in the case of classification setting, okay, so we discussed that there are actually three ways to do classification. You have discriminant based model, then we had discriminative model, then we had generative model, right? Okay. Now, in the case of discriminant based model, like we saw that we can actually use least squares for like classification, right? Like that was called indicator regression. Okay. Now, okay. So now for every model that I'm going to write, like I want you to answer like what is the first term here, the second term here? Is it so you could have LL, which means it's a linear model with linear decision boundary, LN, which means it's a linear model with nonlinear decision boundary, right? Or you could have NL, where nonlinear model with linear decision boundary, or it could be NN, where like it's a nonlinear model with nonlinear decision boundary. Okay, so what is indicator regression? Can someone type in the chat? It's a linear model with linear decision boundary, right? It's a very simple model. Similarly, like we also saw LDA, the Fisher's LDA. In the end of the Fisher's LDA, we saw a way to come up with a threshold so that we can use that as a classifier, right? So now this is also a linear model with linear decision boundary. Okay. Now, what are the discriminative models that we have seen so far in this course? Well, this could be a nice review as well as quiz. So what are the discriminative models that we have seen so far in this course? So can people type? Okay, so logistic regression and k nearest neighbor. Okay, so we have seen logistic regression, which we just saw today, right, on last lecture. And we have also seen k nearest neighbor. K nearest neighbor is also a discriminative model, right? Like because it is just modeling the P of y given x. Okay, now logistic regression. Is it a linear model or a non-linear model? It's not a linear model. It has a sigmoid function in it, right? So it's actually a non-linear model with a linear decision boundary. Okay, or in other words, it's a generalized linear model. Okay, now what about k nearest neighbor? K nearest neighbor is a nonlinear model with non-linear decision boundary. We have seen how complex the decision boundary of can go, right? So finally, we have generative models. Like we have seen a bunch of generative models, but all in one family, right? So the family is called GDA. So we have seen GDA, which is basically a nonlinear model with linear decision boundary, right? Now, if you want to make the decision boundary also nonlinear, you go for QDA. The QDA is nonlinear model with nonlinear decision boundary, right? So then we also had the Nav Base assumption. So there's Gaussian Nav Base and there's also diagonal GDA. So both are nonlinear models, okay, with nonlinear decision boundary here and linear decision boundary here. Finally, we also saw discrete Nav Base algorithm. Okay. This is a nonlinear model with linear decision boundary. Okay. I think that kind of summarizes all the algorithms that we have seen so far. Okay. So any questions on the hierarchy here? So, okay, so what are we going to do for the rest of the course, right? So for the rest of the course, like we would see more algorithms in all these three types of classification categories. And we will also go back to regression at some point again to do more probabilistic regression algorithms. And we will also see few other unsupervised learning tasks in like other than dimensionality reduction. Okay, so are we going to see more unsupervised learning algorithms? Yes, towards the end of the course, like we will see clustering and like a bunch of other things. Okay, so how to choose which algorithm to use when you have so much available, right? Well, I'm not going to give you the recipe because there is no recipe for that. But of course, there's a lot of intuitions on like which is better in what place, right? Like, so for example, like if you remember our discussion on the merits and demerits of all the three types of classification approaches, like that gives you a clue about which type of classifier you should go for your problem at hand. And often you would try few classifiers because the classifier choice itself is going to be the hyperparameter. But again, like it actually comes by practice. Like, so you try a bunch of things and you gain more practical experience. So that is going to help you when coming up with an intuition for which will work in what setting. I would actually recommend you, okay, so for the course, we are going to do a Kaggle competition, but I would actually recommend you to try more Kaggle competitions to get more practical knowledge. Okay, so let's actually, I still have something left for this lecture. Like it's not the end. So we will actually start discussing about discriminant-based classifiers in more detail. Like we spent a lot of time discussing about generative models, discriminative models. So we are going to spend some time for this, like the short time that we have in this lecture and the next couple of lectures about more on discriminant-based classifiers. Okay, so first we are going to start with what is known as the separating hyperplane method. Okay, so this is something that we have already seen, right? Like, so what is the separating hyperplane method? They basically construct linear decision boundary that explicitly try to separate the data into different classes, okay, as well as possible. So basically, the basic idea is very simple. You try to come up with a linear decision boundary that separates the data into as good as possible. Okay, so here is an example. Okay, so here there are two features, x1 and x2, and you want to classify between green and red colors. circles. Okay, so now the orange or the golden line that you see is the solution given by least squares as well as GDA. It's the same solution. Okay, now you can see that this solution actually has some error, right? So what is the error? So it actually wrongly classifies this particular green point, right? On the other hand, I have also plotted two other blue color hyperplanes, right? So if you look at these blue color hyperplanes, you can see that both these hyperplanes have zero error, right? So now the question is, how can I come up with an algorithm which will find these blue hyperplanes? Okay, so now to do this, like we are actually going back in time. So like the very first algorithm which kind of attempted to do this is called the Perceptron algorithm, which was invented by Rosenblatt in 1958. Okay, it's a very simple algorithm. Okay, so given that we have seen logistic regression and other classifiers, now you'll see that how simple this is. So the model is this. So y of x is given by some function of w transpose x. Okay, so a quick note: there is a bias. I'm just not putting the bias separately. So the bias is included in x. Okay, so to make things easier, I'm just putting it as w transpose x. But in reality, it's going to be w transpose x, it's w0. Okay, okay. Now, if it is logistic regression, f is sigmoid, right? Now, instead of that, perceptron uses f, which is basically the step function. So f of a is +1 if a is greater than or equal to 0. Okay, and it is -1 if a is less than 0. Okay, now this is different from sigmoid, right? Like in the case of sigmoid, it gives you a continuous value, but the step function is going to give you a discrete value. It's going to give either +1 or -1. Okay, so now the target, right? So the target classes could be -1 and +1 instead of 0 and 1. Okay, so instead of having 0 and 1, like we're going to consider -1 and +1. Okay, so now this is my model. The next question obviously is, what is the error function, right? So error function, what error function can I use? Okay, so now one obvious error function here is basically the total number of misclassified errors. Okay, so now this is a weird error function. This is not like the least squares or the negative log likelihood. Okay, so why is this weird when compared to those things? Because this error function is a piecewise constant function of w. Okay, so let me tell you why. So maybe it's easier if I draw a picture here. So let's say I have a bunch of circles and a bunch of crosses. Okay, so now let's consider a line which is like this. Okay, now I will try to keep moving this line either up or down. Okay, so now let's say I move this line, let's say I try to move this line like a little bit down. Okay, so now if I move it like this, now there is one more circle which is correctly classified, right? So now the total number of misclassification changes. Okay, so okay, maybe to make things simpler, like to make the point clearer, I'm going to put the circle here. Okay, okay. So now what is the optimal classifier here? The optimal classifier, let me draw that in a golden color. So it's going to be something like this, right? Something which separates both. On the other hand, like what I have now is this black color thing, right? So now I can actually keep on rotating it, right? Like, so now let's say this is time step 1, this is time step 2. Now I could keep on rotating it. This is time step 3. Let me go a little bit down, time step 4, and time step 5, time step 6. Okay, so now you can see that this, after t is equal to 1, when I move to t is equal to 2, my error is going to reduce by 1 point, right? Because one more thing is correctly classified. But between these two red circles, this whole thing, right? There's no change in the error. It's going to be exactly the same, right? So or in other words, if I compute the gradient with respect to this particular error function, that gradient is going to be 0 for all this time. And suddenly when there's one more correct classification, when I jump from this point to this point, like this circle to this circle, I'm going to get a small gradient, right? So or in other words, I say this is a weird error function because in this case, it has discontinuities whenever a change in W causes the decision boundary to move across one of the data points. Okay, so this means that if I use gradient descent, okay, any method that is using gradient information, any method that uses gradient of the error, it cannot be applied. Why? Because the gradient is 0 almost everywhere. Okay, so now how do I solve this problem, right? Like, so like Rosenblatt actually came up with a different way to find the parameters of this perceptron. Okay, so now that let's take the perceptron. So let's compute like what he called as perceptron error criterion. Okay, so what are we looking for? We are looking for some W such that if x of n is in class C1, I want the W transpose xn to be greater than 0, right? Similarly, if x of n is in class C2, I want W transpose x to be less than 0, right? And we already know that t belongs to -1 or 1, right? So now I can actually combine these two things and say, so let's call this as 1 and 2. Okay, so 1 and 2 can be combined. Okay, and say for any x of n, the W transpose xn multiplied by t of n should be greater than 0. Okay, so if it is belonging to -1, -1 multiplied by a negative value will be greater than 0. If it belongs to +1, +1 multiplied by the positive value of W transpose x should be greater than 0, right? So now whenever this condition is satisfied, that means it's correctly classified. Okay, so now he also said if a data point is correctly classified, you have 0 error. Okay, if the data point is wrongly classified, okay, so then you basically want to minimize minus of W transpose x of n t of n. Okay, so now that is the perceptron error criteria. So the perceptron criteria is given as some error function EP of W is given as minus W transpose x of n t of n summation over n belonging to M, where M is all the misclassified patterns. Okay, so M is all the misclassified patterns. Okay, so you can see that this is very much different from the error functions that we have seen so far. So far, whatever error functions we have seen, it is computed over all the training points. On the other hand, the perceptron criteria is computed only over the places where misclassification is happening. Okay, okay, so maybe it was a bad idea for me to start perceptron when I know I cannot finish it in the given time. So I will actually repeat this in the next lecture. Sorry, but we will stop here. I don't want to take more time. Like we will redo Like we will continue from the beginning of Perceptron in the next lecture. Is there any question before I stop the recording? Uh, okay, what is the step size in this case? That's a good point. So we will come to that in the next lecture. It's my bad. I was too greedy to start Perceptron today. I was trying to be on track, but we will do it in more detail next week. Okay, is there any news on the final examination? So that is a very good question. So I think I'm still trying to make up my mind. But one thing that I have kind of decided, and I think most of you also mentioned, is we will not replace the exam with an assignment simply because assignment is going to take more time, and it's a lot of work from your side, also from the TA's side. So we will not replace the exam with assignment. So we are going to do an exam. As some of you might, as you guys might have already received information from Poly. Poly is doing physical exams, but I am trying to not do a physical exam. So maybe by Thursday I will tell you the final answer for intern. But the general but the main message is we are going to have an exam. We are not going to replace it with the assignment. But I will see what is the most convenient way for you, like in terms of like the mode of exam. Okay, so I will stop the recording.